since the first doctor noticed hundreds of years ago that the urine of the diabetic patient tasted sweet. It has been common to call the condition the sugar disease or sugar diabetes, and since nothing was known about physiological chemistry, it was commonly believed that eating too much sugar had led to be the cause, since the ability of the body to convert the protein in tissues into sugar wasn't discovered until 1848 by Claude Bernard. Even though patients continued to pass sugar in the urine until they died, despite the elimination of sugar from their diet, medical policy required that they be restrained to keep them from eating sugar. That pre-scientific medical belief that eating sugar caused diabetes is still held by a large number, probably the majority of physicians. Originally, diabetes was understood to be a wasting disease, but as it became common for doctors to measure glucose, obese people were often found to have hyperglycemia, so the name diabetes has been extended to them as type 2 diabetes. High blood sugar is often seen along with high blood pressure and obesity in Cushing syndrome with excess cortisol, and these features are also used to define the newer metabolic syndrome. Following the old reasoning about the sugar disease, the newer kind of obese diabetes is commonly blamed on eating too much sugar. Obesity, especially a fat waste, and all its associated health problems are said by some doctors to be the result of eating too much sugar, especially fructose. Obesity is associated not only with diabetes or insulin resistance, but also with atherosclerosis and heart disease, high blood pressure, generalized inflammation, arthritis, depression, risk of dementia, and cancer. There is general agreement about the problems commonly associated with obesity, but not about the cause or the way to prevent or cure obesity and the associated conditions. In the earlier newsletter, I wrote about P.A. Pioli in Paris in 1864 and Dr. William Bird in England in 1867, who treated diabetes by adding a large amount of ordinary sugar, sucrose, to the patient's diet. Glucose was known to be the sugar apparently in the diabetes urine, but sucrose consists of half glucose and half fructose. In 1874, E. Karls in Germany reported that diabetics could assimilate fructose better than glucose. In the next decades, there were several more reports on the benefit of feeding fructose, including the reduction of glucose in the urine. With the discovery of insulin in 1922, fructose therapy was practically forgotten until the 1950s, when new manufacturing techniques began to make it economical to use. Its use in diabetic diet became so popular that it became available in health food store and was also used in hospital for intravenous feeding. However, while fructose was becoming popular, the cholesterol theory of heart disease was being promoted. This was the theory that eating foods containing saturated fat and cholesterol caused heart disease. A Swedish physician and researcher, Uffe Lagunskov, has reviewed the medical argument for the theory that lipids in the blood are the cause of atherosclerosis and heart disease, and shows that there has never been evidence of causality, something which some people, such as Broda Barnes, understood from the beginning. In the 1950s, an English professor, John Yudkin, didn't accept the idea that eating saturated fat was the cause of high blood levels of triglyceride and cholesterol, but he didn't question the theory that lipid in the blood caused circulatory disease. He argued that it was sugar, especially from fructose, component of sucrose, rather than dietary fat that caused the high blood lipids seen in the affluent countries and consequently the disease. He was sure it was a specific chemical effect of the fructose because he argued that the nutrients that were removed in refining white flour and white sugar were insignificant in the whole diet. Following the publication of Yudkin's book and coinciding with increasing promotion of the health benefit of unsaturated vegetable oils, many people were converted to Yudkin's version of the lipid theory of heart disease, i.e. that the bad lipid in the blood as a result of eating sugar. This has grown into essentially a cult in which sugar is believed to act like an intoxicant, forcing people to eat until they become obese and develop the metabolic syndrome and diabetes, and the many problems that derive from that. The publicity campaign against saturated fat as an ally of cholesterol derived its support from the commercial promotion of the polyunsaturated seed oil as food for humans. Although the early investigators of vitamin E knew that polyunsaturated fats could cause sterility, and others later found that their use in commercial animal food could cause brain degeneration, there were a few biologists who believed that this type of fatty acid is an essential nutrient. George and Midland Bra had created what they claimed to be a disease in rats caused by the absence of linoleic and linolenic acid in their food. Although well-known researchers had previously published evidence that animals on a fat-free diet were healthy, even healthier than on a normal diet, Bra and his wife published their contradictory claim without bothering to discuss the conflicting evidence. I haven't seen any instance in which Bra or his followers ever mentioned the conflicting evidence, although other biologists didn't accept Bra's claim and several researchers subsequently published contrary results. He later became famous when the seed oil industry wanted scientific seeming reasons for selling their product as an essential food. The fact that eating the polyunsaturated fat could cause the blood cholesterol level to decrease slightly was advertised as a health benefit. Later, when human trials showed that more people on the healthy diet died from heart disease and cancer, more conventional means of advertising were used instead of human tests. But experimental diet consists of purified casein and purified sucrose supplemented with vitamin concentrate and some minerals. Several of the B vitamins weren't known at the time, and the mineral mixture lacking zinc, copper, manganese, molybdenum, and selenium. More of the essential nutrients were unknown in his time than in Yudkin, so his failure to consider the possibility of other nutritional deficiency affecting health is more understandable. In 1933, Barr observed that his fat-deficient rats consumed oxygen at an extremely high rate, and even then the thought didn't occur to him that other nutritional deficiencies might have been involved in the condition he described. Ordinarily, the need for vitamins and minerals correspond to the rate at which calories are being burned. The metabolic rate Barr recalled that the rats on the fat-free diet drank more water, and he reasoned that the absence of linoleic and linolenic acid in their skin was allowing water vapor to escape at a higher rate. He didn't explain why the saturated fat the rats were synthesizing from sugar didn't serve at least as well as a vapor barrier. They're more effective at waterproofing than unsaturated fat because of their greater hydrophobicity. The condensed and cross-linked keratin protein in skin cells is the main reason for the skin's relatively low permeability. When an animal is burning calories at a higher rate, its sweat glands are more actively maintaining a normal body temperature. Cooling by vaporizing the amount of water evaporates is an approximate measure of metabolic rate or of thyroid function. In 1936, a man in Barr's lab, William Brown, agreed to eat a similar diet for 6 months to see whether the essentially fatty acid deficiency affected humans as it did rats. The diet was very similar to the rat, with a large part of the 2,500 calories being provided at hourly intervals during the day by sugar syrup, protein from 4 quarts of special fat-free skim milk, a quart of which was made into cottage cheese, the juice of half an orange, and a biscuit made with potato starch, baking powder, mineral oil, and several and salt with iron and vitamin D and carotene supplemented. Brown had suffered from weekly migraine headache since childhood, and his blood pressure was a little high when he began the diet. After 6 weeks on the diet, his migraines stopped and never returned. His plasma in organic phosphorus declined slightly during the experiment, and his total serum protein increased from 6.98 gram percent to 8.06 gram percent on the experimental diet. His leukocyte count was lower on the high sugar diet, but he didn't experience cold or other sickness. On the normal diet, his systolic blood pressure varied from 140 to 150 millimeter of mercury. The diastolic 65 to 100. After a few months on the sugar and milk diet, his blood pressure had lowered to about 130 over 80 to 88. Several months after he returned to a normal diet, his blood pressure rose to the previous level. On a normal diet, his weight was 152 pounds and his metabolic rate was from 9 to 12% below normal, but after 6 months on the diet, it has increased to 2% below normal. After 3 months on the sugar and milk diet, his weight leveled off at 138 pounds. After being on the diet, when he ate 2,000 calories of sugar and milk within 2 hours, his respiratory quotient would exceed 1, but on his normal diet, his maximum respiratory quotient followed those food that was less than 1. The effect of diabetes is to keep the respiratory quotient low, since the respiratory quotient of 1 corresponds to the oxidation of pure carbohydrate, and extreme diabetic oxidize fat in preference to carbohydrate, and many may have a quotient just below a little or above 0.7. The result of Brown's and Barr's experiment could be interpreted to mean that the polyunsaturated fat not only lowers the metabolic rate but especially interfere with the metabolism of sugar. In other words, they suggest that the normal diet is diabetogenic. During the 6 months of the experiment, the unsaturation of Brown's serum lipid decreased. The author reported that there was no significant change in the serum cholesterol as a result of the change in diet. However, in November and December, 2 months before the experiment began, it had been 252 milligrams percent in 2 measurements. At the beginning of the test, it was 298. 2 weeks later, it was 228, and 4 months later, it was 206 milligrams percent. The total quantity of lipid in his blood didn't seem to change much, since the triglyceride increased as the cholesterol decreased. By the time of Brown's experiment, other researchers had demonstrated that the cholesterol level was increased in hypothyroidism and decreased as thyroid function and oxygen consumption increased. If Barr's team had been reading the medical literature, they would have understood the relation between Brown's increased metabolic rate and decreased cholesterol level, but they didn't record the fact, which is valuable. The authors wrote that the most interesting subjective effect of the fat-free regimen was the definite disappearance of the feeling of fatigue at the end of the day's work. A lowered metabolic rate and energy production is a common feature of aging and most degenerative diseases. From the beginning of an animal's life, sugars are the primary source of energy, and with maturation and aging, there is a shift towards replacing sugar oxidation with fat oxidation. All people are able to metabolize fat at the same rate as younger people, but their overall metabolic rate is lower because they are unable to oxidize sugar at the same high rate as young people. Fat people have a similar selectively reduced ability to oxidize sugar. Stress and starvation lead to a relative reliance on the fat stored in the tissues, and the mobilization of these as circulating free fatty acids contributes to the slowing of metabolism and the shift away from the use of glucose for energy. This is adaptive in the short term, since relatively little glucose is stored in the tissue, and the proteins making up the body would be rapidly consumed for energy if it were not for the reduced energy demand resulting from the effect of these free fatty acids. One of the points at which fatty acids suppress the use of glucose is at the point at which it is converted into fructose. In the process of glycolysis, when fructose is available, it can bypass this barrier to the use of glucose and continue to provide pyruvic acid for continuing oxidative metabolism, and if the mitochondria themselves aren't providing sufficient energy, it can leave the cell as lactate, allowing continued glycolytic energy production. In the brain, this can sustain life in an emergency. Many people lately have been told as part of a campaign to explain the high incidence of fatty liver degeneration in the US, supposedly resulting from eating too much sugar, that fructose can be metabolized only by the sugar. The liver does have the highest capacity for metabolizing fructose, but the other organs do metabolize it. If fructose can bypass the fatty acids inhibition of fructose metabolism, of glucose metabolism to be oxidized when glucose can't, and if the metabolism of diabetes involves oxidation of fatty acid instead of glucose, then we would expect there to be less than the normal amount of fructose in the serum of diabetes, although their defining trait is the presence of an increased amount of glucose. According to Oguagu and Madumere, that is the case. If a fructose deficiency exists in diabetes, then it is appropriate to supplement it in the diet. Besides being one of the forms of sugar involved in ordinary energy production, interchangeable with glucose, fructose has some special functions that aren't as well performed by glucose. It is the main sugar involved in reproduction, in the seminal fluid and intrauterine fluid, and in the developing fetus. After these crucial stages of life are passed, glucose becomes the primary molecular source of energy, except when the system is under stress. It has been suggested that the predominance of fructose rather than glucose in the embryo's environment helps to maintain ATP and the oxidative state. During development in the low oxygen environment, the placenta turns glucose from the mother's blood into fructose, and the fructose in the mother's blood can pass through into the fetus. Although glucose can move back from the fetus into the mother's blood, fructose is unable to move in that direction, so a high concentration is maintained in the fluid around the fetus. The control of the redox potential is sometimes called the redox signaling system, since it coherently affects all processes and conditions in the cells, including pH and hydrophobicity. For example, when a cell prepares to divide, the balance shifts strongly away from the oxidative condition, which increases its ratios of NADH to NAD plus, of GSH to GSSG, and of lactate to pyruvate. These same shifts occur during most kinds of stress. In natural stress, decreased Availability of oxygen or nutrient is often the key problem, and many poisons can produce similar interference with energy production. For example, cyanide or carbon monoxide, which blocks the use of oxygen, or ethanol, which inhibit the oxidation of sugars, fats, and amino acids. When oxygen isn't constantly removing electrons from cells, those electrons will react elsewhere, creating free radicals and reduced ions that will create inappropriate chemical reaction. Stresses and poisons of many different types interfering with a normal flow of electrons to oxygen produce large amount of free radicals, which can spread structural and chemical damage involving all systems of the cell. Ethyl alcohol is a common potentially toxic substance that can have this effect, causing oxidative damage by allowing an excess of electrons to accumulate in the cell, shifting the cell's balance away from the stable oxidized state. Fructose has been known for many years to accelerate the oxidation of ethanol. Oxygen consumption in the presence of ethanol is increased by fructose more than by glucose. Besides removing the alcohol from the body, more quickly, it prevents the oxidative damage by maintaining or restoring the cell's redox balance. The relatively oxidized states of NADH to NADH plus lactate to pyruvate GSH to GSSH system. Although glucose has this stabilizing pro-oxidative function in many situations, this is a general feature of glucose, sometimes allowing it to have the opposite effect of glucose on the cell's redox state. It seems to be largely this generalized shift of cell's redox state towards oxidation that is behind the ability of a small amount of fructose to catalyze the more rapid oxidation of a large amount of glucose. Besides protecting against the reductive stresses, fructose can also protect against the oxidative stress of increased hydrogen peroxide. Its metabolite fructose 1,6-biphosphate is even more effective as an antioxidant. Keeping the metabolic rate high has many benefits, including the rapid renewal of cells and their components, such as cholesterol and other lipids. The proteins, which are always susceptible to damage from oxidants, but the high metabolic rate also tends to keep the redox system in the proper balance, reducing the rate of oxidative damage. Endotoxin absorbed from the intestine is one of the ubiquitous stresses that tend to cause free radical damage. Fructose, probably more than glucose, is protective against damage from endotoxin. Many stressors cause capillary leakage, allowing albumin and other blood components to enter extracellular space or to be lost in the urine. This is a feature of diabetes, obesity, and variety of inflammatory and degenerative diseases, including Alzheimer's disease. Although the mechanism isn't understood, fructose supports capillary integrity. Fructose feeding for 4 to 8 weeks caused a 56 and 51% reduction in capillary leakage, respectively. The ability of the mitochondria to oxidize pyruvic acid and glucose is characteristically locked to some degree in cancer. When this oxidation fails, the disturbed redox balance of the cell will usually lead to the cell's death. But if it can survive, this balance favors growth and cell division rather than differentiated function. This was Otto Berg's discovery that was rejected by official medicine for 75 years. Cancer researchers have become interested in this enzyme system that controls the oxidation of pyruvic acid by the mitochondria. Since these enzymes are crucially defective in cancer cells, the chemical DCA, decoloroacetate, is effective against a variety of cancers, and it acts as reactivating the enzymes that oxidize pyruvic acid. Thyroid hormone, insulin, and fructose also activate these enzymes. These are the enzymes that are inactivated by excessive exposure to fatty acid that are involved in the progressive replacement of sugar oxidation by fat oxidation during stress and aging and in degenerative diseases. For example, a process that inactivates the energy-producing pyruvate dehydrogenase in Alzheimer's disease has been identified. Niacinamide, by lowering free fatty acid and regulating the redox system, supporting sugar oxidation, is useful in those spectrum of metabolic degenerative diseases. A few times in the last 80 years, people have recognized that the hydrophobicity of a cell changes with its degree of excitation and with its energy level. Recently, even in non-living physical chemical systems, hydrophobicity and redox potential have been seen to vary together and to influence each other. Recent work shows how the oxidation of fatty acid contributes to the dissolution of mitochondria. At first glance, it might seem odd that the presence of fatty material could reduce the fat-loving property of a cell, but the fat used as fuel in it is in the form of fatty acid, which are soap-like and spontaneously introduce wetness into the relatively water-resistant cell substance. The presence of fatty acid impairing the last oxidative stage of respiration increases the tendency of mitochondria to release its cytochrome C into the cell in the reduced form, leading to an apoptotic cell death of the cell. The oxidized form of the cytochrome is more hydrophobic and stable. But didn't understand that it was his rat's high sugar diet free of the antioxidative unsaturated fatty acid that caused the extreme high metabolic rate. But since that time, many experiments have made it clear that it is specifically fructose component of sucrose that is protective against the anti-metabolic fat. Also, Brown et al. Want focusing on the biological effect of sugar. Their results are important in the history of sugar research because their work was done before the culture had been influenced by the development of lipid theory of heart disease and the later idea that fructose is responsible for increasing the blood lipids. In 1963 and 64, experiments showed that the effect of glucose and fructose were radically affected by the type of fat in the diet. Although 0.6% of calories as polyunsaturated fat prevents the appearance of med acid, the high fructose diet consistently add 10% or more corn oil or other highly unsaturated fat to the diet. These large quantities of polyunsaturated puffer aren't necessary to prevent a deficiency, but they are needed to obscure the beneficial effect of fructose. Many studies have found that sucrose is less fattening than starch or glucose. That is, that more calories can be consumed without gaining weight. During exercise, the addition of fructose to glucose increases the oxidation of carbohydrate by about 50%. In another experiment, rats were fed either sucrose or Coca-Cola and Purina Cho, or were allowed to eat as much as they wanted. They consumed 50% more calories without gaining extra weight relative to the standard diet. Losing et al. Observed that given a 10.5 or 35% sucrose solution or water and observed that the sucrose increased the energy consumption by about 15% without increasing weight gain. McCall et al. Found that glucose caused a smaller increase in metabolic rate in obese people than in normal weight people, but that fructose increased the metabolic rate as much as it did that of normal weight people. Tapi et al. Saw a similar increase in heat production in obese people relative to the effect of glucose. Brundin et al. Compared the effect of glucose and fructose in healthy people and saw a greater oxygen consumption with fructose and also an increase in the temperature of the blood and a greater increase in carbon dioxide production. These metabolic effects have led several groups to recommend the use of fructose for treating shock, the stress of surgery, or infection. The commonly recommended alternative to sugar in the diet is starch, but many studies show that it produces all of the effects that are commonly ascribed to sucrose and fructose, for example, hyperglycemia and increased weight gain. The addition of fructose to glucose can markedly reduce hyperglycemia during intraportal glucose infusion by increasing net hepatic glucose uptake even when insulin secretion is compromised. Fructose appears most effective in those normal individuals who have the poorest glucose tolerance. Lipid peroxidation is involved in the degenerative diseases, and many publications argue that fructose increases it, despite the fact that it can increase the production of uric acid, which is a major component of our endogenous antioxidant system. When rats were fed for 8 weeks on a diet with 18% fructose and 10% saturated fat, the content of polyunsaturated fat in the blood decreased as they had in Brown et al. Experiment, and their total antioxidant status was increased. When stroke-prone spontaneously hypertensive rats were given 60% fructose, superoxide dismutase in the liver was increased, and the authors suggest that this may constitute an early protective mechanism. When people were given a 300-calorie drink containing glucose or fructose or orange juice, those receiving glucose had a large increase in oxidative and inflammatory stress, and those changes were absent in those receiving the fructose or orange juice. One of the observations in Brown et al. Was that the level of phosphate in the serum decreased during the experimental diet. Several later studies show that fructose increases the excretion of phosphate in the urine while decreasing the level in the serum. However, a common opinion is that it's only the phosphorylation of fructose increasing the amount in the cell that causes a decrease in the serum that could account for the momentary drop in serum phosphate during the fructose load. But since there is only so much phosphate that can be bound to intercellular fructose, it can't account for the chronic depression of the serum phosphate on a continuing diet of fructose or sucrose. There are many reasons to think that a slight reduction of serum phosphate would be beneficial It has been suggested that eating fruits is protective against prostate cancer by lowering serum phosphate. The aging suppressing gene discovered in 1997, named after the Greek life-promoting goddess Clotho, suppresses the reabsorption of phosphate by the kidney and inhibits the formation of the activated form of vitamin D, opposing the effect of the parathyroid hormone. In the absence of the gene, serum phosphate is high and the animal ages and dies prematurely. In humans in recent years, a very close association has been documented between increased phosphate level within the normal range and increased risk of cardiovascular disease. Serum phosphate is increased in people with osteoporosis, and various treatments that lower serum phosphate improves bone mineralization with the retention of calcium phosphate. At high altitude or when taking a carbonic anhydrase inhibitor, there is more carbon dioxide in the body and serum phosphate is lower. Sucrose and fructose increases the respiratory quotient and carbon dioxide production. This is probably a factor in lowering the serum phosphate. Fructose affects the body's ability to retain other nutrients, including magnesium, copper, calcium, and other minerals. Comparing diet with 20% of the calorie from fructose or from cornstarch, Holbrook et al. Concluded results indicate that dietary fructose enhances mineral balance. Ordinarily, things such as thyroid and vitamin D, which improve the retention of magnesium and other nutrients, are considered good, but the fructose methodology allows researchers to conclude, after finding an increased magnesium balance with either 4% or 20% of energy from fructose, that dietary fructose adversely affects macromineral homeostasis in humans. Another study compared the effect of a diet with plain water or water containing 13% glucose or sucrose or fructose or high fructose corn syrup on the properties of rat bones, bone mineral density and mineral content, and bone strength and mineral balance. The largest difference was between animals drinking the glucose and the fructose solution. The rat getting the glucose had reduced phosphorus in their bone and more calcium in their urine than the rat that got fructose. The results suggest that glucose rather than fructose exerted more deleterious effect on mineral balance and bones. An older experiment compared two groups with an otherwise well-balanced diet lacking vitamin D, containing either 68% starch or 68% sucrose. A third group got the starch, but with added vitamin D. The rat on the vitamin D deficient starch diet had very low level of calcium in their blood, and the calcium content of their bone was low, exactly what is expected with the vitamin D deficiency. However, the rat on the sucrose diet, also vitamin D deficient, had normal levels of calcium in their blood. The sucrose likely, unlike the starch, maintained claim homeostasis. A radioactive calcium tracer showed normal uptake by the bone and also apparently normal bone development, although their bone was lighter than those receiving vitamin D. People have told me that when they looked for articles on sucrose in PubMed, they couldn't find anything except article about its bad effect. There are two reasons for that. PubMed, like the earlier index Medicus represents a material in the National Library of Medicine and is a medical rather than a scientific database, and there is a large amount of important research that it ignores. And because of the authoritarian and conformist nature of the medical profession, when a researcher observes something that is contrary to majority opinion, the title of the publication is unlikely to focus on that. In too many articles in medical journals, the title and conclusions positively misrepresent the data reported in the article. When the idea of glycemic index was popularized by dietitians, it was already known that starch, consisting of chains of glucose molecules, had a much higher index than fructose and sucrose. The more rapid appearance of glucose in the blood stimulates more insulin, and insulin stimulates fat synthesis. When there is more glucose than can be oxidized immediately. If starch or glucose is eaten at the same time as polyunsaturated fat, which inhibits its oxidation, it will produce more fat. Many animal experiments show this, even when they are intending to show the dangers of fructose and sucrose. For example, rats were fed diet with 68% carbohydrate, 12% fat, corn oil, and 20% protein. In one group, the carbohydrate was starch, and in other groups, it was either 68% sucrose or 34% fructose and 34% glucose, or 34% fructose and 34% starch. The weight of the fat pad was greatest in the fructose plus starch group and least in the sucrose group. The starch group's fat were intermediate in weight between those of the sucrose and the fructose plus glucose group. At the beginning of the experimental diet, the average weight of the animal was 113 grams. After 5 weeks, the animal in the fructose plus glucose group gained 164 grams. Those in the sucrose group gained 177 grams, and those in the starch group gained 199 grams. The animal ate as much of the diet as they wanted, and those in the sucrose group ate the least. The purpose of their study was to see whether fructose causes glucose intolerance and insulin resistance, since insulin stimulates appetite and fat synthesis. Reduced food consumption and reduced weight gain showed that fructose was protecting against these potentially harmful effects of insulin. Much of the current concern about the danger of fructose is focused on the cornstarch-derived high fructose corn syrup. Many studies assume that its composition is nearly all fructose and glucose. However, analyzed sample of it before and after hydrolyzing it in acid to break down other carbohydrate. They found that the carbohydrate content was several times higher than the listed value. Underestimation of carbohydrate content in beverage may be a contributing factor in the development of obesity in children, and it's especially interesting that so much of it is present in the form of starch-like material. Many people are claiming that fructose consumption has increased greatly in the last 30 or 40 years, and that is responsible for the epidemic of obesity and diabetes. According to the USDA Economic Research Service, the 2007 calorie consumption as flour and cereal product increased 3% from 1970, while added sugar calorie decrease 1%. Calories from meat, egg, and nut decrease 4%. From dairy food decrease 3%, and calories from added fat increase 7%. The percentage of calories from fruit and vegetables stays the same. The average person consumed 603 calories per day more in 2007 than in 1970. If changes in the national diet are responsible for the increase of obesity, diabetes, and the disease associated with them, then it would seem that the increased consumption of fat and starch is responsible, and that would be consistent with the known effect of starch and polyunsaturated fat. In monkeys living in the wild, when the diet is mainly fruit, their cortisol is low, and it rises when they eat a diet with less sugar. Sucrose consumption lowers ACTH, the main pituitary stress hormone, and stress promotes increased sugar and fat consumption. If animals' adrenal glands are removed so that they lack the adrenal steroid, they choose to consume more sucrose. Stress seems to be perceived as a need for sugar. In the absence of sucrose, satisfying this need with starch and fat is more likely to lead to obesity. Glucocorticoid hormone inhibits the metabolism of sugar. Sugar is essential for brain development and maintenance. The effect of environmental stimulation and deprivation stress can be detected in the thickness of the brain cortex as in little as 4 days in growing rat. These effects can persist through a lifetime and can even pass on transgenerationally. Experimental evidence shows that polyunsaturated fat retards fetal brain development and that sugar promotes it. These facts argue against some of the current popular idea of the evolution of the human brain based on ancestral diets of fish or meat, which only matters as far as those anthropological theories are used to argue against fruits and other sugar in the present diet. Honey has been used therapeutically for thousands of years, and recently there has been some research documenting a variety of uses, including treatment of ulcers and colitis and other inflammatory conditions. Obesity increases mediator of inflammation, including the C-reactive protein and homocysteine. Honey, which contains free fructose and free glucose, lowers CRP and homocysteine as well as triglyceride, glucose, and cholesterol, while it increases insulin more than sucrose did. Hypoglycemia intensifies inflammatory reactions, and insulin can reduce inflammation if sugar is available. Obesity, like diabetes, seems to involve a cellular energy deficiency resulting from the inability to metabolize sugar. Sucrose, and sometimes honey, is increasingly being used to reduce pain in newborn for minor things such as injections. It's also effective in adults. It acts by influencing a variety of nerve systems and also reduces stress. Insulin is probably involved in sugar analgesia as it is in inflammation, since it promotes entry of endorphin into the brain. An extracellular phosphorylated fructose metabolism, diphosphoglycerate, has an essentially regulatory effect in the blood. Another function metabolite, fructose diphosphate, can reduce mast cell histamine release and protects against oxidative and hypoxic injury and endotoxic shock, and it reduces the expression of the inflammatory mediator. inflammatory mediated TNF-alpha, IL-6 nitric oxide synthase, and activation of NF-kappa B, among other protective effects, and its therapeutic value is known, but its relation to dietary sugar hasn't been investigated. A daily diet that includes 2 quarts of milk and a quart of orange juice provides enough fructose and other sugars for general resistance to stress, but larger amount of fruit juice, honey, or other sugars can protect against increased stress and can reverse some of the established degenerative conditions. Refined granulated sugar is extremely poor, but it lacks all of the essential nutrients, so it should be considered as a temporary therapeutic material or as an occasional substitute when good fruit isn't available or when available honey is allergenic.